So I want us to have a go at this first rates of reaction question, right? So in order to determine the effect of concentration on reaction rates, the reaction between butyl chloride and water is investigated. So here we have this entire reaction here, right? As 0.1 mole per dm cube aqueous solution of butyl chloride is reacted with water, and the concentration measured at various time intervals to produce results in table 2. All right, so those are the results. Now what we're supposed to do for 4 marks is to plot a graph of the concentration of butyl chloride on the x-axis against the time in seconds on, well, on the y-axis rather, against the time in seconds on the x-axis, right? So first question of the morning, are we capable of doing this? Are you guys confident in plotting graphs? That's fairly straightforward, isn't it? Is it not? Yes, no, maybe, kind of. Go ahead. Somebody raise their hand. Okay, somebody texted. All right, so it's easy. All right. So this graph is rather easy. The time in seconds are going well. It starts small, right, and then the time increases as we go down. Same with the concentrations change, was actually decreasing as we go down, right, and the rates will also be affected as they decrease going down, right. So generally, the graph that we're going to get, how the graph would look here. Yet again, this is on a screen, so it's not going to be the prettiest thing ever, right? I'm just going to draw, I'm just going to sketch what the graph should look like. So the graph is going to end up, should I draw up once again? Probably should. All right, so the graph is going to look like this. So it's going to be a generally, okay, what's happening to the screen? All right, so this is how the graph would generally look. So we're gonna have the x-axis, well, the y-axis, or we're gonna have the x-axis, right? The thing is, we're plotting time against generally the concentration of the thing, right? So the concentration, CONC, against concentration, right? Based on the fact that the values are decreasing specifically, our graph is going to look something like that, right? So that's generally just a sketch of how the graph would look. The graph is going to look something like that, right? Based on the fact that they're going to decrease in that linear way, we're just going to have a negative line of best fit, right? Based off of the information here. But I do believe that you guys have the capability to draw graphs. That's completely fine, right? Using the graph, estimate the concentration of butyl chloride at T equals 100, well, 400 seconds. How do you guys do that? How would we be able to do that?
So you would extrapolate it from the graph?
Extrapolate from the graph, lovely. Right, so even though I've only made a mere sketch of the graph, right, let's say that, let's just say arbitrarily, that 400 seconds is around here. Let's say that that's 400 time in seconds, right? All we're going to do is, as we said, extrapolate from the graph and then come across the concentration. That's all we're gonna do. So after we draw our graph, that's what we do, and that concentration here, x, would be our value. All right. Rather simple question coming from rates of reaction. All right. Very simple. draw a graph, extrapolate to find the concentration at 400 seconds. All right, so that's 5 marks just free. 5 free marks to gain towards your distinction. All right, so that's not a problem at all. For this now, in addition, sorry, to concentration, catalyst and temperature also affect the rates of reactions, right, or reaction rates. Using suitable, well-labeled diagrams, explain how each of the following affects rates of reaction. So, how do catalysts affect rates of reaction? Go ahead.
So can you explain how we extrapolated the graph, please?
Explain how. All right. Okay. So going back to the graph, this is just a sketch, obviously. Right, so what's gonna happen, after we draw our graph and everything, we're gonna get this negative line of best fit here, right? And that line will show the proportionality between the concentration, right, and the time, right? So it's going to show that proportionality between the concentration and the time, right? So that means at this point in the graph, right, let's say this point in the graph, at this given time down here, we're going to have the concentration here. So we're basically going to be extrapolating like that. So the line is showing us our proportionality between concentration and time. So at any point on the curve itself, right, that's the given concentration time, right, relating to that singular point is going to be what we're going to be using. So if we're asked to get the concentration at 400 seconds, as we saw from down here, right, if we extrapolate up, if we draw a line from 400 going directly until it touches the curve, right, then the horizontal now, right, will be our concentration. Does that make sense? Is that a little bit clearer now? So wherever touches the curve. So if 400 touches the curve there, whatever concentration touches the curve here is the concentration of 400 seconds.
Okay, thank you.
Right? And as it relates to what's happening here now, catalysts, right? Guys, you guys can still see my screen, hopefully, because I'm not sure why it comes off sometimes. All right, so concentration and the catalyst, right? So okay, how does, not concentration rather, but catalyst and affecting the rate of reaction? How do catalysts affect the rate of reaction?
It creates an alternate pathway.
It's an alternate pathway, lovely. All right. So when we add catalysts, right? No, how does that affect the rate? Go ahead. What type
It
of reaction?
speeds up the reaction while also lowering the activation energy.
All right, lovely. So we know a general, let's have this general graph here, right? Where we have the concentration of catalyst increasing, right, on our y-axis. So we're gonna have our catalytic concentration, catalytic concentration, right? And here we have the rate. So how does the rate increase with the concentration of catalysts, right? We're going to have something like this. Does that graph look familiar? Right, so if we increase the catalytic concentration, that's going to increase the rate specifically, right? As we increase the amount of catalysts, right? And then there's going to be an equilibrium set up. Well, not really an equilibrium set up. There's going to be a plateau, right? As increasing amount of catalyst won't necessarily affect the rate of reaction. Does that make sense?
Yes, sir.
Yes, sir.
All right. So it's just explaining how that affects. So as catalysts tend to decrease our activation energy by introducing alternate pathways, right? So hopefully we can understand that through Hess's law, we produce alternate pathways to get to the same product, right? And with that, we're gonna increase that general rate, right, of reaction specifically. So catalyst will increase rate of reaction until the reaction rate reaches some amount of plateau, right? Because at a certain point, you can increase the amount of catalyst, but that won't necessarily affect the rate of reaction. All right. So generally, that should be how it is written there. That should be generally 4 marks for your explanation there. And then here we have temperature. How does temperature increase the rate of reaction? Or how does rate of reaction increase with temperature?
So don't forget the how it provides more.
Repeat?
I said don't forget that it provides more successful collisions with the catalyst.
Oh, the catalyst. Okay. So if we let's go into collision theory then. All right. So as it relates to collision theory, I'm not really looking at the thermodynamics of the reaction itself, right? So we know that, as you stated, it allows for more collisions, right? More successful collisions, right? So that means that what happens generally with the catalysts, right? Catalysts tend to combine to the substrate molecules, right? And then that it holds it in place, right, for actual collisions to occur, right? So usually in reactions that we've looked at before, right, there are catalysts themselves that allow our that act as a reaction center, right? So if you increase the amount of catalysts, right, you increase the possibility for these different combinations, right, as relates to collisions in collision theory, right? So that's how catalysts really work, right? They tend to bind to whatever we're working with, right? And that creates an alternate pathway, right, for new collisions to occur, right? And that will increase the rate of reaction as these alternate pathways are of a lower energy, right? So that's generally what's happening with catalysts. Thank you for reminding me of that. And if we're going to be using that for our catalyst specifically, with our temperatures, we have to be mentioning collision theory as well. That would be the kinetic theory as it relates to rates. And we know that temperature, as the temperature increases, the rate of reaction is going to be increasing like that, right? So let's say that the rate is here, right? And let's say that the temperature is here. So as temperature increases, the rates continuously increase along that proportion, along that line of best fit, right? Direct proportionality. And we know why, because if we increase the temperature, right, which is just the increase of the kinetic energy within a system, right, the molecules are going to be moving faster, right, and with more energy. And that's important as it relates to the Boltzmann distribution curve, right? So if we use even a Boltzmann distribution curve, we'd understand that if we increase the temperature, there will be more molecules that's more molecules that have more of the suitable energy, right, that can result in more successful collisions, right? So for good measure, let me just draw the Boltzmann distribution curve for catalysts up here, right? So for the catalysts specifically, let's say that we have a general catalytic reaction, right? And let's say that this is the activation energy. There's activation energy, right? Let's say that this is the activation energy here. So energy of activation energy, right? So you have to pass the activation energy for these molecules over here, right, to be reacting, right? What happens when we add a catalyst now, right? If we are to add a catalyst, what it generally does is decrease the activation energy, right? So let me not do it like that. Let me move the activation energy line, right? So let's say that this is the kinetic energy of the reactants, right? Let me use black for this, right? So let's say this is speaking to the kinetic energy of the reactants, right? The successful collisions. If we actually increase the activation if we decrease the activation energy, right, from that regular EA here, let's call that EA1, right, and we decrease it now to EA2, this is what we're going to be happening. That's what's going to be happening, right? So without a catalyst, right? So this is without a catalyst. So this is no catalyst. Right? So no catalyst here, but this is with catalyst. So with a catalyst, right? So what's going to happen here, without catalyst, only the shaded area there in blue will have enough energy to react, right? But with a catalyst, it's going to allow even more molecules to have suitable energy for a reaction to occur, right? Everybody remembers the Boltzmann distribution curve, right? So hopefully that is something that you guys do remember, right? So we have that there. Okay, so that's gonna be what happens with the catalyst, allowing for more molecules to reach suitable activation energy, right? But when we talk about temperature now, temperature has a shift, right, with the graph specifically. I'm just hopefully assuming that you guys remember how the temperature graph would look. How would the temperature graph look? All right, I'm not hearing anyone. So the graph of the Boltzmann distribution
Can you
curve,
repeat the question, sir?
I was asking how the temperature graph would look. All right. So let's say that we have an activation energy here. Let's call this the activation energy EA, right? So with catalyst now, we decrease the activation energy, right? So we shift the activation energy line. But with temperature now, it doesn't change the activation energy. So let's say that we have an initial temperature, right? Let's call this initial temperature T1, and let's say that T1 exhibits a temperature around 25 degrees Celsius, right? So this shaded area now will be the amount of energy, or amount of molecules per se, that have reached sufficient activation energy and will give us successful collisions, right? What happens here now, if we increase the temperature, let's use a red or an orange, right? If we increase the temperature now to T2, let's say that T2 is now 40 degrees Celsius. We're just using random values. It's now increase the temperature, right? What we're going to have is something like this. So if we increase the temperature now, more molecules would have enough energy, right, for successful collisions. And that is how temperature affects the successful collisions as it relates to the rate of reactions, right? So I drew both the regular rate catalytic curve and the Boltzmann catalytic curve, as well as the regular rate temperature curve and the Boltzmann temperature curve, right? So 4 curves were drawn and explained. So hopefully that information is sufficient. Are there any questions?
No, sir.
All right. Name 2 industrial processes in which catalysts are used. Any 2? Two industrial processes where catalysts are used.
Catalytic cracking.
Okay. Cracking, right? So you have catalytic cracking. Lovely. What else? Give us another one. There are many, millions upon millions of reactions and processes that use catalysts industrially. Name some.
Would breaking long carbon chains count as one?
That is what cracking is. So cracking is one. What else is present? What could we use catalysts for? Nobody has any other idea about the process. Nobody here did Unit 2 before Unit 1. In that case, you'd have a lot of processes. The Haber process. We use iron. Right? In cracking, what do we use? We use zeolite.